All right, this one's a little different. Number 2 here is an architect is designing a new hotel that will be 200 feet tall and has a building footprint in the shape of a T. It will be located in an area that is prone to earthquakes. Which of the following design strategies would be the most appropriate? So this one is one, before we start even really trying to answer, we have a couple of things like the T. We know there's some worries there. That's going to come up. But we really have to take a quick look at the answers to really understand what the question is really getting at. Because this one is, all the excitement is actually in the answers. Yeah. So let's take a quick look at the answers and then we'll come back and think about it. So A, possible, is provide a double height ground floor entrance. Interesting. B, use exterior shear walls. All right. C, provide balconies. D, isolate the two portions of the T footprint from each other. All right, so looking at this, what are the key parts that jump out at you?
The key parts is, they give you, a lot of times these questions, they give you more information than you really need. Whether it's 200 feet or 22 feet, the answer is the same. So don't get bogged down in some of the extra information that's provided. The other thing is, in the shape of a T, why is that important? And so, some of these questions that you'll get, you're not going to be doing seismic design on the exam, but these conceptual things will definitely be on the exam. And with the T, it's trying to tell you that we have irregularities. So in an ideal world, in earthquake, we'd have a perfectly square building that with no transfers, all the columns are exactly the same.
Or a nice circle.
Or a nice circle, that works out too. But unfortunately, that's not the structural world that we live in.
And why a square? Like, what's the advantage?
The advantage of a square is that A, you don't have reentrant corners, which this T shape does.
So that's these little inside corners here, right there. And there.
Right. And then you don't have to worry about things like generally like torsion, other irregularities that we would have to design for. And we're not saying that you can't do this. It's just we take design penalties as engineers to be able to design for this.
So what's a layman's version of torsion? It's like kind of twisting.
Yep.
So if the earth is shaking around, right, and it's shaking that way and a little bit this way and this way, the worry here is these big corners start shimmering and shaking around, and that you start getting these guys doing a little limbo dance kind of thing going on, and you're putting a huge amount of pressure on those corners, right? As the building is, because it's weighted differently on the different parts of the T, there's more of a pull, more of a twist as it goes along, and so you end up with these kind of hard to judge forces in these sort of unusual spots, especially in those interior spots. There's a number of places where it could become a problem if the T was really long.
Yep.
Then, if you had the building going way out over here, then this would be just a much bigger lever arm, if you will, and so it'd be more twisty out there. Yep. So there's a lot of different potential problems, but the obvious one that we see when we see the T shape is that reentrant corner. Did I say that right?
Yes,
Reentrant
you did.
corner? Okay, I always get that wrong. So the first thing you noticed was the T, and you're starting to figure out, all right, what of that is going to be the big issue?
So so I think if you see these reentrant corners, you're trying to make these shapes basically into most regular that you can, and by looking through these answers, it'll give you a clue as to which one would be the best. So like the first one, for example, is a double height ground floor entrance. Those are things we try to avoid as engineers. It gives you a soft story, we call it.
But we love them as architects.
Yes, you do.
Right? Every lobby in the city wants to have that double height first floor.
Which we can in Chicago, but if you're
because there's not a lot of earthquakes.
So if you're building this in, Los Angeles, for example, then you can't have, we have to take penalties for this grand entrance to the buildings.
And because the issue is that double height thing, it means you're putting a huge amount of pressure onto those columns.
Right.
And as this big weight of the upper building, in the upper floors, if it's only, 13-foot floor to floor or something like that, those columns don't have a huge amount of kind of twisting going on.
Right.
But you got one that's 25 feet long or 30 feet long for one of those columns, and then you have this huge weight of a building on top of it, and it's shaking around. That's just it's called a soft floor because you're worried it's just going to collapse.
Right, right.
You've used the phrase design penalty a couple times.
Yes.
What does that mean?
Oh, so it means instead of designing that column for the load that it sees, we would have to, in order to be able to accommodate and not collapse, we would have to design for something 2 to 3 times what that load is. And so
So like the load that we just calculated, for example, going down, like you would just ignore that almost for those things because there's going to be this other issue which is going to make those particular columns much, much more robust.
Right. And so that's why, when I have friends from California visiting us here in Chicago, even if they're looking at a building that I designed that was 50 stories tall, they're like, oh, your columns are so cute.
That's funny.
Because we don't have to take those kind of seismic penalties here.
Okay, thank you.
So okay, we've gotten rid of A because that's creating a soft story, which is a bad idea. What about B?
Well, use exterior shear walls. I am all on board for using exterior shear walls and having all my resistance out in the exterior. But I have a feeling that as architects, you guys might have something to say about that.
What with the fact that it's hard to put windows in it?
Yes.
Yeah. So there's issues. The shear walls. That's a possible answer.
It's a possible answer, but
So maybe we'll skip by that one for the moment.
Yep.
All right. Provide balconies.
Provide balconies. It's not doing anything. It's not helping. It's not. That's like a null answer. It's not helping us. It's not hurting us.
I mean, it's great if you're trying to barbecue some ribs or
Sure.
something, but not really helping us in any other real way.
Right.
So we're going to get rid of that. All right. How about D?
D is isolate 2 portions, and that is the answer. And so what you'll end up having structurally is 2 separate buildings. When we design, we'll look at each part of that T as 2 separate buildings. And why that's important for you guys architecturally is that you will have to make accommodations in the floors and in your exterior facade to sort of hide that part.
So we're literally building 2 separate buildings
Right.
and then kind of doing a little jig here to kind of give them something that can accept movement in
Right.
between.
So you'll, as structural engineers, we'll provide you with how far that distance needs to be. And then it's up to you to create these beautiful joints that so that you can't see those gaps between the 2 buildings.
And what would be a typical number?
For a 200-story building,
I mean, just rough justice. Are we talking 5 feet? Are we talking 5 inches?
yeah, we're talking inches probably, 10 maybe inches sometimes on a taller building. But we have to take into account accommodate both the movement in the top of the T and the sort of the stem of the T, and be able to provide enough space so that they don't knock into each other.
And they're both moving.
Yes.
Which is one of those things you forget. You look at it in one way and you think, oh, all right, I've got it all calculated.
Yep.
But then you're like, oh, wait, the other one's moving as
The
well.
other one's moving too.
Yeah.
If you've ever been in a building, right, and you've walked over one of those metal plates on the floor, you perhaps are standing over a movement joint, and there's a cover over that. And if you look, you'll see that it's on the floor. And then if you look at the wall, usually it runs up the wall. If you look at the ceiling, usually it runs up the ceiling. Once you sort of realize that this is a thing that sometimes happens, that you have one building, but it's kind of broken into 2 pieces, you'll see those movement joints that are hidden. And as you guys are saying, usually sometimes they're a half an inch, sometimes they're a couple inches. Just depends on.
And they might be hidden very well. You might
Right.
have clever little overlapping
Yes.
walls or something like
Right.
that, so it's harder to tell.
Mm-hmm.
Or they might be hidden more cheaply, and you
Right.
go around to Home Depot and get a little cover plate and kind of screw it on. Yeah,
You can see it the easiest in airports because airports
are
are so
so
long.
big.
Yep.
Yeah,
And you'll see going from terminal to terminal that there's a lot of those floor covers and wall coverings and such.
So what we're recommending is that the next time you see one, rip it off and look.
Right, take a look,
Inside,
yeah.
see if
Measure it,
yeah, There's probably a movement joint in there.
Yep.
yeah. Tell them Mark Tier sent you.
Yeah. Don't call us.
All right.